Test 1 2 3. Test 1 2 3. Good morning or afternoon, everyone. My name is HAIRI by MUSLIHIN, and today I'm pleased to present our case study on project planning and execution for the Advanced Cable Diagnostic and Localization System. This project was undertaken in collaboration with Integrated Development Network Sdn Bhd. So for the next slide is project planning. So let's start with why this system is crucial. Underground medium voltage and high voltage power cable form the backbone of our electrical grid. However, conventional maintenance methods face huge limitations. They cannot accurately detect hidden insulation degradation. They risk permanently damaging edges SLPE cable insulation through aggressive high-pot DC testing. They rely heavily on the manual interpretation of wave reflection, and they often lead to delayed fault detection, unexpected outage, and soaring repair costs. To solve this, we developed the SCDLS disadvantage system combine them alternating current DAC testing with time domain reflectometry TDR and partial discharge PD. Analysis to identify and locate defect before catastrophic failure occurs. Our primary objectives are to generate, control DAC high voltage test wave, accurately detect and map PD activities, locate exact insulation defect using TDR, and sharply reduce diagnostic processing time through a centralized database that automates report generation. Our project scope seamlessly cover everything from installing the DAC excitation system and setting up HFCT sensor to configuring centralized fault location mapping and reporting platform. So as you can see from the point there, 1 2 3 4. For the first one is background, and for the second one is objective, and for the third one is project scope, and lastly is problem statement. So that's all for the point that I has explained before. So we going to the next slide. So for the working principle in and technical flow. Moving on the core engineering of our system, the entire diagnostic process follow a strict 6-step workflow to guarantee safety and precision. So for the step 1 is cable isolation and safety preparation. Safety is always our highest priority. We switch off both the remote and test end. Confirm the cable is completely de-energized using a phase indicator. Apply a ding, discharge remaining energy with a discharge rod, and implement strict lockout or tag out procedure. So for the second step is the TDR test. We connect time domain reflectometry clip to the cable core, red, yellow, blue phase to map out the physical line. By identifying wave reflection peaks, we calculate the absolute cable length and precisely map the exact physical distance of cable joint or structural discontinuities. And so for the step 3 is the insulation resistant IR test. This is simple test. Using a 5 kV mega, we inject high voltage DC across the phase to check for fundamental insulation breakdown, recording specific resistance value over 30 second and 60 second interval to calculate the polarization index and the dielectric absorption ratio, or we call it DAR. So for the step 4 is OWTS or DAC connection and calibration. So here we hook up the high voltage injection cable to test object. We input the cable physical parameter into our software, configure the velocity propagation 160 millisecond, and calibrate our equipment to synchronize range across the line. So for the step 5 is the DAC partial discharge test. we progressively ramp up voltage step on each phase from 0.5 U0 up to 1.7 U0. We actively monitor the line to capture the exact partial discharge inception voltage, or we call it PDIV, when activity starts, and the exit station voltage, or we call it PDEV, when it's dropped. So for the last step is step 6, obviously. So for the step 6 is result analysis and evaluation. We cross-reference our TDR, IR, and PD result against standard criteria. Cable are categorized as healthy, or we easily call it fit for service, suspect elevate PD, monitor or retest, or defective, high PD or poor IR, do not energize immediately, repair required, or we call it NWT. So we going to the next slide. So for this slide is executives. A specialized project like this requires a highly coordinated team structure led by our director Nazlin binti Abdul Wahab and principal engineer R.I. Rohaizat Hashim. Our operation are split cleanly into cable diagnostic, transformer diagnostic, and condition-based maintenance. I operate directly within the cable diagnostic engineering tier to deploy this technical solution. So as you can see, this is our organization chart. So we going to the next slide. So in this slide 5 is for the Gantt chart, looking at our scheduling, the execution span across an intensive timeline. Initial site visit, proposal, and hardware acquisition took place in the opening weeks. This was rapidly followed by sensor setup, system integration, TDR calibration, and software UI validation, concluding with final system validation and asset handover. So you can see the slide, the item there, the status there, and the duration of our completion status. So we go into the next slide. So the next slide is to demonstrate the scope of deployment. Our engineering field target involve 5 distinct substation nodes covering 5 critical circuit feeders across locations like SSU Subang and SSU Shah Alam. This represents a total of 15 target measurement points using combination of high frequency current transformer, sensor, and DAC or TDR. You need to pull dense environmental data across transformer termination, switchgear joint, and mid-span joint bay. Okay, do you still with me or I don't care? So we're going to the next slide. So for the next slide is very basic for this system. We call it equipment. So in this, you can see a four equipment that important in our system. So to achieve this high level of diagnostic accuracy, we created a highly specialized array of hardware. Let me break down the critical function of each piece of equipment utilized in this project. So for the right top is called DEM-SC testing system. This is the core power engine of the project. Its function is to generate the control high voltage DEM-SC test wave need to stress the cable insulation naturally without wearing it down like traditional DC testing. So for the next equipment is Mega. We call it Mega. It's a very, what is it called? It's a very common things in electrical. So we use specifically during step 3, its function is to inject a high DC voltage to measure the bulk resistance of the cable insulation. It's verify basic safety and check if the cable can withstand voltage before we reach applying a major DAC load. So for the left bottom, we call it on-site, or the easiest way, TDR, or time domain reflectometer. This as our radar system. Its function is to transmit a low voltage electrical pulse down the cable and look for reflection caused by the impedance change. This allows us to map out total cable length and pinpoint the exact physical location of cable faults and join down the meter. So for the next equipment is bottom left. I'm sorry, for the TDR is right bottom, and for the next item is, or equipment is, partial discharge calibrator at the left bottom. So this is our measurement baseline tool. Its function is to inject a known precise charge packet into the cable network prior to testing. This calibrates our sensor just for signal attenuation over long distance and ensure the tiny partial discharge we detect later are accurately quantified in pinoculums. So I'm going to add on some equipment or accessories. So for the next equipment is it doesn't show in this slide, so I'm going to tell it. So for the next slide is for the next equipment is high voltage test lead and accessories. Their function is to provide highly shielded, safely insulated pathway to transmit high voltage testing signal from our diagnostic card to the cable core without leaking signal or introducing external noise. So for the lastly is grounding equipment and safety PPE. Somewhere like glove, mats, barrier, or anything else. So this is very simple in electrical. So their function is absolutely critical, providing a low impedance path to earth to safely discharge a static or store energy post-test, ensuring total physical protection for our testing crew working around high voltage equipment. So that's all for this slide. So we're going to the next slide. Okay, as you can see, this is a budget planning that I have told you from the next slide with the equipment slide. So we're moving next to the project result. So for the project result, this implementation of the SCDLS yield remarkable operational insight. We achieve pinpoint accurate PD magnitude measurement, precise cable fault mapping via our automated TDR, and validated insulation condition before high voltage was ever introduced. The key takeaway from this project is the immense value realized. We drastically improve the network reliability of underground medium and high voltage asset, reduce unexpected grid failure via predictive maintenance, and significantly minimize human calculation error by utilizing automated TDR wave analysis. Most importantly, we have successfully moved asset management from a high-cost reactive model to a highly efficient proactive model. So, moving on to the last slide. So, as you can see, we have same project result. So, as you can see in the point there, we have CQI to monitor, SOP, and our future plan. So, to ensure the long-term reliability of this system, we have institute a continuous quality improvement, or we call it CQI framework. We regularly validate TDR accuracy, benchmark our process directly against international IEE and IEC standards, and update historical hotspot maps. We have also established comprehensive technical manuals, engineering training, protocol, and strict high voltage SOP. Looking ahead, our engineering team plans to expand this diagnostic platform beyond partial discharge monitoring. We aim to integrate distribute temperature sensing, monitoring, and dissolved gas analysis to establish a truly comprehensive, smarter predictive maintenance framework for highly value grid asset. So that's all for my slide or for my presentation. With that, I conclude my presentation. Thank you very much for your time. I would now like to open the floor to any technical question you may have when I arrive back at my study places. We call it UTM. So thank you.